Welcome back. Over the past sets of lectures, we have looked at different ways of describing data. Today, we're going to focus on another type of descriptive statistic which lets us go beyond simply looking at how often a score occurs, and it's going to move us towards looking at inferential statistics, which is what we'll be turning to in the sessions to come. Now, when we talk about frequency distributions, we have one here. We've looked at one similar to this in the past. We can talk about how often each score occurs. For instance, in this graph here, we see that 1 occurs about 3 to 5 times, whereas 5 occurs closer to 55, and 6 occurs about 75 times. So rather than thinking about how often a score occurs, which is what we're talking about with the frequency, we could also think about how likely a score is to occur. Now, this is the idea of probability. Now, if the very sound of the word probability scares you, you are not alone. It kind of starts to bring up the scary stats stuff, but let's break it down a little bit further. Now, let's say I asked you, looking at these scores, how likely is it that a person scores 1 out of 10 on positive emotion? So, based on this data, you'd say actually it's not very likely because there's only 3 out of all of these people that scored a 1. In contrast, if I asked you how likely is it that they scored a 6 or a 7, then you say actually much more likely because there's a lot more scores that are falling there. So from here, we could actually ask, what's the probability that a score or a set of scores occurs? Probability ranges from 0 to 1, and so 0 means there's no chance that it could occur, and 1 means 100% chance. So if you find that the decimals a little confusing, just remove the decimals and think about it as 0 is 0%, 0.5 would be 50%, 10, or 1 would be 100%. So you can think about it in terms of percentages. Now, this gives us a rough estimate of the probability that a score occurs based on the actual data that we've collected. So this this kind of estimate is based on what's called an empirical distribution. So it's a distribution scores based on actual data that we might have collected. Now, we can actually be more precise in terms of our estimates. For any score that occurs, we actually could calculate the probability that it would be a certain score. We think about where it falls underneath a curve, and we could calculate that actual number. Now, if this starts to really scare you, don't worry. We won't make you do that. Now, I certainly wouldn't want to spend my time trying to figure out all of these numbers, but some people in the past have. Statisticians spent their PhD or their career creating theories and using math to create distributions of scores that occur. So these are essentially idealized versions of these distributions, and these can be called theoretical distributions based on theory, also called probability distributions. Now, there's a lot of different distributions we might have, but probably one of the most common probability distributions is what's called the normal distribution. Now, we've looked at other graphs that are relatively normally distributed. It looks sort of a bell shape, peaking in the top, falling down to either side. But the actual normal distribution, this theoretical distribution, has certain special features. In particular, as we see in this graph here, it has a mean of 0 and a standard deviation of 1. Now, this is an interesting feature that actually lets us do something very interesting in this. This is what's called a z-table. It's been calculated using this distribution, and what it says is it indicates the probability that a certain percentage of scores falls above or below a score. For instance, if we look in this table, a z-score in this first column corresponds with 93.3% of the distribution is below that number, and about 6.7% of the distribution is above that. And so we can see that in the table there. So we can use that to figure out where a score falls compared to the rest of the distribution. In fact, for any data that we have that's relatively normally shaped, that has a mean of 0 and a standard deviation of 1, we can use that table to say what's the probability that a certain score will occur. Now that sounds great, except for the fact, if we think about most of the scales that we use in psychology, most of them do not have a mean of 0 and a standard deviation of 1. Think about it. On a 1 to 5 scale, how is your health? On a 1 to 7 scale, how satisfied are you with your life? And none of these actually have 0 even within the possible values. Now, fortunately, there's a way around this. Any scale that we have can be converted to this normal distribution by calculating something called a z-score. This is also called standardizing a variable, what it does is we're converting it to a standard scale that has a mean of 0 and a standard deviation of 1. Now, how do we calculate this? Here's our formula. And so the z-score, we take the score, we subtract out the mean, kind of mean centering it, and then we divide by the standard deviation of the set of data that we have. And so this gives you what's called a z-score. Now, once we have this z-score, there are a couple things that we can do with it. So it's fairly straightforward to calculate, and then it's helpful as well. Let's go back to this table. Now, I said if we know a z-score, we can figure out how many scores are above it, or what percentage is above, and what percentage is below. And so once I calculate a z-score, I can look exactly at that. How much of the data is below that? How much is above that? Now, when we think about values that are above and below, and I won't go into the details now, but there are a couple numbers that we particularly pay attention to. A z-score of 1.96 is important, and the reason for that is that 2.5% of the data is above that. Now, because it's symmetrical, we can say that negative 1.96, 2.5% is going to be below that. And so what we get to is that 95% of the population is going to fall between a negative 1.96 z-score and a positive 1.96 z-score. Now, just hold on to the information for now. We'll come back to it when we actually talk about inferential statistics. A few other things we see here is that within one standard deviation of the mean is about 68% of the population, and it extends out from there. Now, the other thing we can do with z-scores is compare two values. So, for example, here are two test scores. We can compare them. Now, let me give you an example of this. Let's say I give a person a well-being questionnaire, and they get a 4. Is that a good thing? Or is it a bad thing? It all depends on the scale. If it's on a 1 to 5 scale, then 4 out of 5 is pretty good. If it's on a 10-point scale or a 100-point scale, then a 4 actually could be pretty bad. So what we can do when we calculate z-scores is we put them on the same scale, and then we can directly compare them. Let's look at an example. Let's say I have two students, Ted and Harry, and they're both in the middle of the semester. They each take a midterm exam in their respective courses. On Ted's biology test, he scores 45 points. On Harry's stats exam, he scores 40 points. Who did better on the exam? Now, obviously, if I look at 40 and 45, 45 is clearly higher than 40. But let's see how they compare with others in their class. In Ted's biology class, the average was 51, and so Ted scored below average. In stats, the average was 36, so Harry actually was better than average. So if we directly compare them, when we actually say, okay, one is below and one is above the mean, they're not directly comparable. But what we can do is calculate their z-scores, as I have here. So we take the raw score. For Ted, it's 45. For Harry, it's 40. We subtract out the mean from their class and divide by the standard deviation for their class. Doing this, we clearly see that Ted had a z-score of -6, while Harry had a z-score of positive 3.64. He clearly did better because that z-score is much bigger compared to his class. Now, it's easiest to get your head around this actually practicing with this, looking up things in the table, seeing how scores can actually compare. I've included some sample problems on my website that you can check out if you want to try these. So the normal distribution allows us to consider the probability that a score occurs. From that, z-scores give us a way to put different measures on the same scale, which has a mean of 0 and a standard deviation of 1. Once we have it as z-scores, we can also look at the proportion of scores that are above it and the proportion of scores that are below that. Now, next time, we'll actually use this as we start to look at the relationship between two variables. Thanks for listening. See you next time.